In this video, I will show you that symmetry and group theory are directly related. Let's take an equilateral triangle as our example for symmetry. We say this triangle is symmetric because it's equilateral, but a better way to describe its symmetry is to look at all the actions that can keep this shape unchanged. We can rotate this triangle for 120 degrees, and that will keep the triangle unchanged. Or we can also rotate it by 240 degrees. That will also keep this equilateral triangle unchanged. And we can rotate for 360 degrees, but that's the same as not doing a rotation. So we can have a do-nothing action that keeps the triangle unchanged. So these three actions are all the actions we can do to this triangle that keeps this shape unchanged. To further describe the symmetry that this triangle has, we can consider acting another action on this triangle after the first action. So we can act a first action first. This is our first action. Then after the first action, we can do a second action and discuss what is the overall effect of having these two actions in a row. So all the three actions we have are here, and let's see what will happen if we first rotate the triangle by 120, then we rotate again by 120. We know that will give us a overall 240-degree rotation. So acting 120 after 120 gives us 240. And if we act 240 after 120, then together that's a 360 rotation, which is the do-nothing rotation. So acting a 240 after 120 gives us the do-nothing action. Similarly, we can look at how the overall effect will be if I rotate 120 after 240. After 120 and 240 and 120 is again 360, so it's going to be the do-nothing action. And if I rotate 240 after 240, that's 360 plus another 120. So together, I get a 120 rotation. The action of doing nothing after something is simple. You just do nothing after the first action, and doing nothing first then doing something is also simple. You just do the second thing as the overall effect of two actions in a row. So discharge of the possible actions we can do to keep the triangle unchanged, and the relation between the actions is a more specific way we can describe the symmetry that this triangle has. Now, I will show you that this way of describing the symmetry is going to be the same as having a group. So what is a group? A group is a set. Let's call this set G. A set is just a collection of things, and we're going to say we collect these three actions to be a set. These three actions is inside our set, and other thing is not inside our set. Now, we call the elements inside the set actions. And let's use small g for the symbol of this action. So these three are like G1, G2, G3, and they are inside a big set G. And we need to define an operation. Let's call this operation dot. And this will just be acting a second action after a first action. and we want the set and this action together to satisfy 4 conditions. The first one is closure, which means that if I have 2 elements inside the group, let's say G1, G2 are both inside the group G or the set G, and here we can say G1, G2, these 2 actions is inside the set G, then acting G1 after G2 or G2 after G1 together is a effective action. We can act any action after a first action, and we see that together the overall effect is also 8 actions we can do on the triangle. The thing is that this G3 need to also be inside the set big G. And we see that indeed, no matter how we act the second action after the first action, the result, the overall effect, will always be one of these 3 actions. So the overall effect will always be inside the big group G. So indeed, if we define our group element in this way, then it automatically satisfies the closure. The second one is associativity. This means that if we want to act 3 actions in a row, then acting the first 2 together first and figure out the overall effect, then act on G3 should be the same as figuring out the overall effect of 2, 3 first, and then act on G1. Now we can just look at the example over here, and let's randomly call this 1, 2, and 3. Then we can let's look at the effect of acting 1 after 2. So 1 after 2, 1 after 2. This is the second action, first action. So 1 after 2 give us this guy. So this is the overall effect of 1 after 2. Now let's act that overall effect after 3. 3 is this guy. So 3 is our first action now. 1 after 2 is this guy, which is this guy. So 1 after 2 together after 3 give us this guy. So this is 1 after 2 after 3. Now let's do the same thing, but for 2, 3 first, then act G1 after it. So 2 after 3, 2 after 3, 2 after 3 is this guy. So this action is the same, is the overall effect of 2 after 3. Then let's look at 1 after them together. 1 after 2 after 3 give you this. And you see indeed 1 after 2 after 3 and 1 after 2 then 3 give you the same overall effect. So our group elements defined in this way also satisfies associativity. The next one is identity. We need to have an element 1 inside our group, and this element need to satisfy that all the group element acting after this give you the group element itself. And we do have this identity element, which is our do nothing action. So that's why I put that action, do nothing action inside our table, because then it will satisfy the identity axiom of the group theory. Finally, we need to have invertibility. Which means that there's always an element called G inverse inside the group, such that the G inverse after G will give you the identity element for all the group elements. So you see that for all the group elements we have for all these three actions, you can find an action acting on it such that it gives you back the identity element. So indeed, the group, so indeed if we define the actions acting on a symmetric object as our group, then it is indeed a group that satisfies all the four axioms that a group should satisfy. So we see symmetric and symmetry and group theory are directly related. And physics is about finding symmetry, and we define all the actions that we can do on the symmetry of our universe, and that is group.